talking about this problem, which is very similar to like one of the last problems on the web work homework. We were trying to, in fact, I will share, I imagine most of you have seen this, but just in case you haven't, that's weird. I'll let you go. Let me share this with you. Right, so we're just looking at essentially a problem like this. We've got a function. I picked the function 2x plus 3 on the interval from 0 to 4. We first divided it into n subintervals, which had a length of 4 over n, and you can't see that very well. In order to determine an overestimate for the area, we use the right endpoint. So for the kth interval, that ended up being k times 4 over n, or k times delta x more generally. And this is actually the formula, it's a plus k times delta x, where our a value is 0, right? Because the interval is from 0 to 4, or a to b. And then we wrote down the Riemann sum, which is this notation here. And I'm going to stop sharing my screen now. So this notation here, this sum from k equals 1 to n of f of k times 4 over n. Oh, I forgot one thing in my Riemann sum there. I forgot the 4 over n out front. Which it's okay to put that, you can move constants in and out of a sum just fine. And as far as this sum is concerned, the only thing that is variable is k. K is the only thing that's changing. N is a constant as far as this summation or sigma notation is concerned. So what this means, if I write it all out, and I am going to write it up, is it's going to be, you know, I'm actually going to write that here. It's 4 over n times f of 1 times 4 over n, so just 4 over n, plus 4 over n times f of 2 times 4 over n, plus 4 over n times f of 3 times 4 over n, all the way to the very last one, which is when we get to n. So we get to 4 over n times f of n times 4 over n, which is just f of 4. So basically, I just want to remind you, right, we are just finding all the areas of the rectangles, right? This first expression, 4 over n times 4 over n, is just the area of this first right-hand rectangle. 4 over n times f of 8 over n is the second right-hand rectangle, and so on. All the way to the kth one, all the way to the very last one. Right, that last one is 4 over n times the height, which is f of 4. Now, we're not actually going to write this all out because it's really kind of messy and unnecessary. So we're going to talk about now how you actually use some of the formulas that were given to evaluate this expression or to simplify it. So let's go to the other side here. Do stop me if you have questions. So how do we calculate the sum? The sum from, and I forgot, let me actually, I forgot the 4 over n. No, I don't want that. I don't want this to be like that. So how are we going to calculate that? Well, we're going to use some rules of sums. So I'm going to show you some steps we can take here, and then if you have questions, let me know. So I'm going to simplify all of this a little bit. I'm going to write this as the sum from k equals 1 to n. And distribute this 2, so that's going to be 2 times k times 4 over n. So that's going to be 8 over n times k plus 3 all times 4 over n. That's going to be the sum from k equals 1 to n of 8. Sorry, I'm going to distribute this 4 over n. So actually you can get 32 over n squared times k plus 3 times 4 over n is going to be 12 over n. Okay. If you're doing this sort of process, one thing I've noticed over the years doing it is that whenever you have terms like this, if you want this to work out the way it's supposed to work out, the power of n that you have should always be 1 larger than the power of k in the same term. So here I have a k to the first and an n squared, great. Here I have a k to the 0th and an n to the first, great. That's always something that we need to be true for this particular process to work the way we expect it to. All right, so now I'm going to do a couple of things. I'm going to break this up into two sums. So I'm going to write this as the sum from k equals 1 to n of 32 over n squared times k, plus the sum from k equals 1 to n of 12 over n. And then for this one here, I'm going to factor out the constant. So the sum from k equals 1 to n. Oh, sorry, I forgot to factor out the constant. So again, the only variable here is k. So I'm going to factor out everything that's not k. So I'm going to have 32 over n squared times the sum from k equals 1 to n of k. Plus, I'll factor out the 12 over n, why not? 12 over n times the sum from k equals 1 to n of 1. Cool so far? Questions about this? Okay. So now here's where we have to use a formula. The formula is given in the problem, but here's what it is. This, in fact, let me just write it down below here. So we can talk more about this if we need to. The sum from k equals 1 to n of k is n times n plus 1 over 2. The sum from k equals 1 to n of 1 is just n. This one's especially easy to see because this one, there's nowhere to plug in the k. So this one here is just, well, you plug in k equals 1 and you get 1. Plus you plug in k equals 2 and you get 1. And then you plug in k equals 3 and you get 1. And you do that n times. So if you've got 1 n times, that adds up to n. So that one's pretty easy to see. So let me ask you guys, do I need to clarify this formula anymore? Or is everyone, so n, what is n? That's a good question, Sophia. What is n? N is the number of subintervals. So n is any positive integer you want it to be. N could be 5, n could be 1 billion, but it's not a specific number. What we're gonna do in the next step after this is we're going to take the limit as n goes to infinity. Because the idea is that, right, if we've got all these rectangles, right, there are, and another way, a better way to answer your question is n is the number of rectangles we have divided up the area into. And so what we're going to do is we're going to let the number of rectangles get infinitely large, meaning there's going to be an infinite number of rectangles, and they're all going to have an infinitesimal width, so that our approximation of the area becomes the actual value of the area, because we're not going to have any errors because each of those rectangles is going to be super duper narrow. So I want to reiterate though. Does anyone want me to clarify this formula, or is everyone cool with that? I'm happy to talk about it, but if I don't need to, I won't. Okay. Do I have room? Yeah, I can erase this. I don't need this here. Okay. Someone showed me a really cool way of doing this one time. I forget what it is. Oh yeah, I know what it is. So I'll give you a real number example and then more of a whatever example. So let's say I want to add up 1 through 10. Now I know the answer is 55 because I've done this, I know this formula, right? So the answer is 10 times 11 divided by 2. N times n plus 1 over 2. But here's a faster or another way to see it. So this is equal to, I think it's 55. Let's pretend like we don't know for a second. It's supposed to be 55. Well, I'm going to do the same thing but backwards. 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 equals the same thing, right? Right. So now if I add this way, what's 1 plus 10? Yeah, thanks. What's 2 plus 9? Oh, someone, oh, again. What's 3 plus 8? Right, they're all going to be 11. How many 11s are there? How many numbers are there? Yeah. Now, if I add this and this, I also have to add this and this. So I have 10 11s. So I can write this as 10 times 11 equal to twice the unknown number, and then I can divide by 2. And that's 55. And this would work if we went up to 10 or we went up to n. And I can do the same thing. I say, okay, 1 plus 2 plus 3 plus 4 plus all the way up to n, and then flip it, n plus n minus 1 plus n minus 2 plus all the way to 1. Add this way, 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. N minus 1 plus 2 is n plus 1. N plus 1 is n plus 1. It's equal to twice the unknown amount. And then I have n plus 1s. How many n plus 1s do I have? How many n plus 1s are there? Yeah, n, exactly. So this whole thing is n times n plus 1. It's equal to twice the unknown amount. So the unknown amount, which is 1 plus all the way to n, is n times n plus 1 over 2. Pretty cool. So that actually shows us that this sum is really n times n plus 1 over 2. Cool stuff. Cool. So we're going to apply it right now. So here's the idea. So this thing right here, the whole reason I factored out the 32 over n squared is so I could have just that. Because if I look at that, that's 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to n. Okay, that was the other thing I was wondering if I needed to talk about. So there are some rules for sums, which, yeah, so we should definitely talk about that for just a minute. So let's say, let me just throw up let me just throw up. Let me throw up some examples. Let me not throw up. Throwing up is not a good plan. Let's have the sum from k equals 1 to 6 of 2k plus k, believe it or not. Looks terrible. Come on, James. Of 2k plus 5. So what I want to point out is there are two operations with sums that you're always allowed to do. You can always break up a sum, or so like if there's addition or subtraction, you can break it up into two different sums. So I can break this up as this. And then I'm also allowed to factor out any constant multiples. Now let me show you why. So what I'm saying is I can get to this. Here's why we're allowed to do this. Let me just write this out. So if I plug in k equals 1, I get 2 times 1 plus 5. If I plug in k equals 2, I get 2 times 2 plus 5. If I plug in k equals 3, right, it goes on a bit. K equals 4. let's stop at 4. 4 is enough. 4 is enough to see what we're trying to get at here. I'm going to change it to 4. Sorry. We didn't write that in a whole lot of 6s. 4, 6. Okay, so check this out. I'm not going to actually simplify these things. What I'm going to do is I'm going to first put all the 2 times whatever's together. So I can write this as 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. And then I can also write the 5 plus 5 plus 5 plus 5. Okay, what can I factor out from this? Exactly, right? I can factor out any constant multiple, because what happens is if you've got a constant multiple, when you actually write out the sum, that multiple is multiplying each of the k values. And so when I have each of my k values, they're all going to get multiplied by 2. So it's perfectly fine to factor out. And then you're right, I could also factor out a 5. You're not wrong, right? I could totally factor out a 5 and write this as 5 times the sum of 1. And a lot of people do that. And then I think I can squeeze this in down here. This is 2 times 1 plus 2 plus 2 plus 4 is the sum from k equals 1 to 4 of k. And 1 plus 1 plus 1 plus 1 is the sum from k equals 1 to 4 of just 1. Do you do that with the b minus a over n? No. Well, yes. Yes, I did. So let me actually show you what I did. So first, before we move on, let me just make sure everyone's okay with this, right? We can take some expression, some sum of k equals something to something, and we can basically break it up into a lot of pieces and then factor out all the constants. So let me just show you one more example that we're not going to actually work out. I'm just going to show you that if I had something like the sum from k equals 1 to 7 of, I don't know, let's say 2k squared plus 1/3 k minus 6, I could totally break this up into 3 sums. The sum from k equals 1 to 7 of 2k squared plus the sum from k equals 1 to 7 of 1/3 k plus the sum from k equals 1 to 7 of -6. And then furthermore, I could then factor out anything that wasn't a k. So I could write this as 2 times the sum from k equals 1 to 7 of k squared plus 1/3 times the sum from k equals 1 to 7 of k plus, or really I would say -6 times the sum from k equals 1 to 7 of 1. So we're allowed to pull out anything that isn't a k, or more generally anything that isn't whatever you're using as your index down here. So sometimes it's like I or j, or m or n sometimes even. All right, so here's what we did. So you are right to ask, could I have pulled out the b minus a over n? And you're right, I could have. I could have at the very beginning said I'm going to factor that 4 over n out in front. Instead, I decided to distribute it because I knew eventually I was going to want to simplify it. So I simplified this part, and then I multiplied it through. But then after I multiplied it through, then I factored out the constants that I had. Okay. So I think we're ready then to say that, okay, so I can walk you through this. I multiplied this through, right, simplified it. I broke it up into 2 sums, and then from each of those sums, I factored out the constant not k thing. And then we are, did you have a question, Sophia? I see your hand raised.
Yeah, what do you mean by you multiplied it through?
So I just mean I simplified this, right? So I first did 2 times k times 4 over n and got 8 over n k. plus 3. And then this 4 over n is multiplied by all of this. So I distributed it, or I multiplied it through all the terms. Is that all right?
Yeah.
Okay. I should have said distributed. That's a more mathematical term. Okay. So then we factored out the constant terms, and then we used the formula that we just talked about. The sum from k equals 1 to n of k is n times n plus 1 over 2. And the sum from k equals 1 to n is just n. Sorry, the sum from k equals 1 to n of 1 is just n, because you're just adding up 1 n times. All right, and now here's the real truth. I don't really want to simplify this. We could simplify it. There's not a lot of simplifying to do. If you wanted to, you could write this as, I don't know, I guess I could write this as 32 times n squared plus n over 2n squared plus 12. I definitely don't want a common denominator. I really just want to leave this as, I guess, 32n squared plus 32n all over n 2n squared plus 12. Okay, here is the last question, which is the really important part. What's the limit as n goes to infinity of this expression? 32n squared plus 32n over 2n squared plus 12. It's actually one of my favorite numbers. 8's my favorite, but this isn't 8. Does anybody know what this ends up being? 28 is correct. Yes. So how did Morgan get 28? Because that seems like it just appeared out of nowhere, maybe. So obviously there's the 12 here, and the 12 was good. The limit of this is 32 over 2, which is 16. And what I imagine Morgan is doing is recognizing that we have a rational function where the degree on top and the degree on the bottom are both the same. And when the degrees are the same, the limit to infinity is the leading coefficient on top divided by the leading coefficient on the bottom, which is 32 over 2. It's exactly like how I imagine most of you know that the limit as x goes to infinity of 3x to the 4th plus 2x plus 1 over 7x to the 4th minus 5x cubed plus x squared plus 2. All of you know that that limit is equal to what fraction? Is it 3/7? Yeah, it's 3/7. And you could either use L'Hopital's rule, or you could do the thing where you divide the top and bottom by x to the 4th, and then you see that you get 3 over 7, and all the other terms go to 0. But really, you don't have to do any of that. You just get to know that as long as the degrees are the same, you get to have the quotient of the leading coefficients. So this is going to be 16 plus 12, which is indeed 28. Let's check our answer. We're going to check it in 2 different ways. Yeah, I'm going to leave this up here for a second. So one way to check our answer, and again, so I'm going to start using some integral notation. So we just found the area under y equals 2x plus 3 between 0 and 4, right? We just found this area here. And so you could, if you wanted to, if you really like the trapezoid area formula, you could use the trapezoid formula to find the area of this. That's a formula that I never really remember. I am going to try and make my life easy. If I'm going to find the area of this using geometry, I'm going to break it up into a rectangle and a triangle. So this rectangle, what's the area of that rectangle? What's the base of this rectangle? What's the height? It's not quite 8. 8's actually the height of the triangle. So I know my drawing is not to scale. This part is 8 because, oh, maybe my writing is not very good. That's not an 8 there. That's actually a 3. Sorry about that. If that's what was causing the mistaken identity here, that's a 3. So the height of the triangle is 3. Yeah. No, I understand. My writing is not always the best. So the rectangle has an area of 12. And now again, I will point out my drawing is really not to scale. The triangle has an area of base is 4, height is 8, but it's 1/2 base times height, which is going to give you 16. So the area is indeed 28. We can see using geometry. Great. Okay, and then here's the other way we're going to start calculating area under curves by using what's called the definite integral. So the way you express the area under a curve and above the x-axis is by writing the integral from your leftmost endpoint to your rightmost endpoint. So from 0 to 4. If you're actually trying to write area, the leftmost endpoint should always go on the bottom. The rightmost endpoint should always go on top. Sometimes they get out of order for other reasons, but generally it's left to right is bottom to top. And then the function, 2x plus 3 dx. Okay, here is the way you use the definite integral to actually, well, I should say, here's the way you use the fundamental theorem of calculus to find the area under a curve. You anti-differentiate this function. What's the antiderivative of 2x? Or another way to ask that, yeah. What's a function whose derivative is 2x? It's x squared. What's the antiderivative of 3? Yeah. If it's a definite integral where you're finding area under a curve, we don't have any need for a plus c. So we find our antiderivative, and then we evaluate it at the rightmost endpoint, and then we subtract and evaluate it at the leftmost endpoint. So it's going to be, I'm going to plug in 4, and you get 4 squared plus 3 times 4, minus I'm going to plug in 0, and you get 0 squared plus 3 times 0. And that ends up being 16 plus 12 minus 0, which is 28. So we've seen 3 different ways to calculate the area under a curve, and they all gave us the same number, which is good because it would be worrisome if they didn't. I saw, Sophia, did you have your hand raised, or was it just your previous hand raised?
I don't remember what I was going to ask.
Oh, I'm sorry. Well, if you remember, feel free to ask. So I think we should work through another example, one that has a square in it. So let me, let's see. What do I want to do here? Oh, sorry. That's important. Sure, let's do. Sorry, sometimes these get kind of gross.
I remember.
Go ahead.
Why don't we add plus c?
One question. Let's say we did. If I add a plus c, when I plug in 4, I get 4 squared plus 3 times 4 plus c. And when I plug in 0, I get 0 squared plus 3 times 0 plus c. And so then when I calculate this, I get 16 plus 12 plus c minus 0 plus 0 plus c. And the c and the negative c always end up canceling out. So you could write a plus c. It's perfectly fine to write a plus c, but it's always going to turn out that the plus c is going to cancel with the other plus c.
That makes sense. Thank you.
So yeah, it's perfectly fine to do that, but it's unnecessary. So let's look at another example. So I want to, again, go through the same process, which is called the limit definition of the integral to calculate the area under the curve of x equal to 4x minus 3x squared between x equals 0 and x equal to, let me think for a second here, 1. And so let me say a few things. First, we can express this using an integral. We're going to do all the things, but you can write this as that the area is equal to the integral from 0 to 1 of 4x minus 3x squared dx. And let me actually make sure they get the dx on the other one. Yeah. I want to emphasize that when you see this notation, all this notation means is this squiggly s thing here means integrate. This dx means with respect to x. And then these limits of integration means plug in 1, subtract 1, plug in 0. We can also draw a picture. 4x minus 3x squared. Why did I pick something that gross? Sure. If I plug in 0, I get 0. If I plug in 1, I get 1. And the vertex of that parabola would be negative 4 over 2 times negative 3 would be like 2/3. So the vertex is probably like here-ish. It's probably like something like this. And then we continue on that way. So we're trying to find this area. And I will point out that unlike the previous example, we can't use geometry really to find the area here. And that's not totally true. There are geometrical methods to find the areas under quadratic formulas or equations, but that's not really the point here. Morgan, I don't think I have answer keys on Canvas, but there are answer keys on Grant's website. Which is, so if you're looking for answers to those questions, you can find them at Grant's website, which is where I get lots of my source material. Wow, Lab. Yeah, of course, no problem. Can you guys hear when I take a screenshot? Does it make the camera sound for you guys, or is it just me that hears it? Okay. Well, so we're going to go through the whole process of the same sort of like problem 27 or 25 or whatever from web work. So I'm going to divide this into n subsections, each with 1 over n, or 1 minus 0 over n, if you like. And then in order to determine an overestimate for so that question is not as true here, because using the rightmost endpoint isn't always going to give us an overestimate. That's okay. It is perfectly fine to always use right, or always use left, or always use kind of anything. Because here's the thing. What we're doing is we are breaking this up into some number of rectangles. Let me grab a garbage pen over here. And so we're breaking this up into some rectangles. I'm going to pretend like I'm using right endpoints. And the thing is, it doesn't really matter if we're using right or left or some point in the middle, because as we let the number of intervals, that is the number of rectangles, get larger and larger and larger towards infinity, the width of each rectangle gets super duper narrow. And so the error that each rectangle has, whether it's an overestimate or an underestimate, is going to end up not being an error anymore because of how infinitesimal their widths become. So I'm just going to use the right endpoints. And you should, if you're ever not sure which endpoint to use because no one has specified something, it is good to default to the right endpoints because they're usually the easiest to work with. So to answer the next question, the first rectangle, the right endpoint, is going to be just 1 over n. Right? If I'm breaking up the interval from 0 to 1 into n subintervals, right? Here's x sub 0, here's x sub 1, here's x sub 2, here's x sub k minus 1, here's x sub k. I'm going to give myself more room just to make it so it looks. Here's x sub n minus 1, and here's x sub n, which is 1. All right, so the first subinterval, the right endpoint is x sub 1. The second subinterval, the right endpoint is x sub 2, and so on. And x sub 1, right, this length is 1 over n, so it's 1 over n. This length is 1 over n, so that's 2 over n. So x sub k is looking like k over n. Right, because we've just gone 1 over n over k times, right? 1 over n plus 1 over n plus 1 over n plus 1 over n plus 1 over n. K times is going to give you k times 1 over n, which is k over n. Okay, so what is the area? So let's look over here. Let's say this is my kth subinterval. The area of that kth subinterval is the base. The base width is 1 over n times the height. And the height is f of x sub k, which in this case is f of k over n. Questions about this? Okay. So now we're going to write our equation for the approximate area, or the Riemann sum, using right-hand endpoints. And I guess I'll have to go to the other side. All I'm really going to do is use the sigma notation. In fact, I'm going to write it all out. So here's our picture. I'm gonna make it big. Right, so we've got x1, x2, all the way to xk minus 1, xk, all the way to xn. That's x sub 0 is 0. So now let's do that. So this is the kth rectangle, and just like I said here, right? There's the area of the kth rectangle. So my total area approximation is what I usually call R sub n for the approximated area using right-hand endpoints with n subintervals. It's not R for Riemann, it's R for right. Some people, you can also do ln as well, and mn for left and midpoint. So the area of the first rectangle is delta x, or 1 over n, times f of x of 1. The area of the second rectangle is base 1 over n times f of x of 2, plus all the way to the area of the kth rectangle is 1 over n times f of x of k, plus all the way to the last rectangle is going to be 1 over n times f of x sub n, which is 1, f of 1. But I don't want to write all that, right? We don't want to write all that. What I should have done is just said, oh, look, Rn is 1 over n times the sum from k equals 1 to n of f of x sub k. Right? Same thing, much more compact. Sorry, someone was just, yeah, all right, apologies. So then we're actually going to use the function. Remember that the function is, what is the function? I think it's 4x minus 3x squared. That sounds right. Yeah, it is. So this is going to be, oh, and I suppose I should say, and x sub k is also k over n. So this is going to be 1 over n times the sum of 4 times x sub k, right? Not x, but x sub k, minus 3 times x sub k squared. And now we're going to use our rules for sums to break this up into things we can deal with. So I'm going to simplify this a little bit. Oh, sorry, I forgot that k equals 1 to n. So this is 1 over n times the sum from k equals 1 to n of 4 times k over n is 4 over n k, right? And I'm going to break this up into minus 1 over n times the sum of 3 times k squared over n squared. I could have brought the 1 over n inside, but I didn't really need to because remember, eventually we're trying to factor everything out that's not a k. So factor out the 4 over n. You get 4 over n squared times the sum from k equals 1 to n of k minus 3 over n times n squared is n cubed times the sum of k squared. And I will remind you that we are looking good because our power of n in the denominator is always 1 larger than our power of k in the numerator. N squared, k to the first, n cubed, k squared. So that looks like we're going to be safe. So let's say we're going to run out of room. Yeah. Sure. So here's what we've got. We have 4 over n squared times the sum from k equals 1 to n of k minus 3 over n cubed times the sum from k equals 1 to n of k squared. We know this formula. We talked about it last time, earlier today. So we get 4 over n squared times n plus 1 over 2 minus 3 over n cubed times, there is also a formula for the sum of k squared. In fact, there is a formula from k equals 1 to n for really any positive integer power of k. K squared, k cubed, k to the fourth, et cetera, et cetera, et cetera. The formula for the sum from k equals 1 to n of k squared is a little bit less easy to actually prove to you, but I can tell you that it is n times n plus 1 times 2n plus 1 all over 6. And we can talk more about that if you guys want me to, but we could also just take it for what it is. All right, and I really don't think you want to simplify this at all. because that's not really the point. So usually when I've done work like this, I'm going to show you what I would usually do. I would say that here's what I would have actually done, just to kind of go back a little bit. I would have been saying this whole time that the integral, or the area under the curve, from 0 to 1 of 4x minus 3x squared dx is equal to the limit as n goes to infinity of this expression, which is equal to the limit as n goes to infinity of this expression, which is equal to the limit as n goes to infinity of this expression, which is equal to the limit as n goes to infinity of this, which is equal to the limit as n goes to infinity of this. And now here's the thing. We can take this limit real easily. For this first piece here, I'm not going to multiply it out because I don't have to. I can see that if I did multiply it out, I'd get a 4n squared as my leading term on top. And on the bottom, I would get a 2n squared. So since I have a 4n squared over 2n squared, what's the limit of this part going to end up being? Why do we want the limit? Because the limit is how we actually calculate. Again, so let me back up. The reason we want the limit as n goes to infinity is because that's the n going to infinity is what's saying the number of rectangles is increasing and the width of each rectangle is getting smaller and smaller and smaller, so that we're not going to have these little errors anymore, right? We're going to have infinitesimally small rectangles that actually give us the actual area under the curve. So taking the limit as n goes to infinity moves us from an approximation to exactly finding the area. It's kind of like in Calc 21A, when we find the slope of the secant line, and then we take the limit of that slope to find the slope of the tangent line. The secant line slope is this approximating slope that's closer and closer to the actual slope, but we have to take the limit as our value gets closer to something so that we get the actual slope. Okay, so back to this question, you guys. What's the limit of just this part? It's an integer. It's not very big. You guys are close, but you're not quite there. So let me point out. So if I multiply this out, yeah. So I would have the limit as n goes to infinity of 4 times n squared plus n over 2n squared. And now I think it's a little easier to see that this part's going to be 2, because it's 4 times n squared over 2 times n squared. And 4 over 2 is 2. So again, when I'm looking at these rational expressions, I'm just looking for the coefficient of the highest power in each of the top and the bottom. So for this next one, I really don't want to multiply this one out. If I were to multiply it out, what's the highest power going to be? N to the what power? Exactly, n to the third. So in the denominator, this is an easy question. This is like everybody should be able to get this question right off. What's the coefficient of n cubed going to be after I multiply this out? So just me and Crystal now? Oh, Sophia too. Okay, cool. Right, it's going to be 6. Okay, harder question. If I multiply out the top, what is the coefficient of n cubed going to be? So don't forget, we've got this part and this part. Hopefully you guys can see it all right. Yeah, I think you were missing the 3 before. Exactly. So if you look at this part here, if you multiply this part out, you're going to get 2n cubed plus some smaller terms. And then if you multiply that by 3, it's going to be 6n cubed. So our answer here is going to be 2 plus 1, which is 3. And that is actually the area under this curve. Okay, Sophia, do you want to expand on that a little bit?
I understood when you said like the 4/2 part.
Okay.
But then you went back and then I didn't understand anything after that.
Okay, sure. So so what I'm trying to do here, I'm really trying to be lazy, but really what I'm trying to do is to show you how you don't have to do a ton of multiplying because we don't want to. So I could multiply this out, right? I could multiply this out and get, over there I'd have 4n squared plus 4n all over 2n squared. And if I multiply this out, on the bottom I'm going to get 6n cubed. On the top, let's see, I've got 3 times n. And here I've got n plus 1 times 2n plus 1, which is 2n squared plus 2n plus n is 3n plus 1. And if I multiply this all out, 3n times 2n squared is 6n cubed. 3n times 3n is 9n squared. 3n plus 1 times 1 is 3n over 6n cubed. And then we can use the fact that we talked about before, which is that you've got a limit to infinity of a rational function where the degrees are the same, meaning the highest power on top and the highest power on the bottom are the same. The limit of that is the fraction or quotient of the leading coefficients. So the limit of this part is 4/2, because the leading coefficient on top is 4 and the leading coefficient on the bottom is 2. And the limit of this part is 6/6. So that's what's going on there. But what I want you to be able to do and so you don't have to do all this, is to look at this and see, okay, well I can see I'm going to have an n times a 2n times a 3. That's going to give me a 6n cubed as my leading term on top. And same deal here, I'm going to have a 4 times an n times an m, that's going to give me a 4n squared. And I don't have to multiply out the whole thing to know what the leading term coefficient is going to be. Are there other questions about this? Okay. Can you go to the other side? Yes. I think I was actually on this side. Yeah, oh no, it's right there. There we go. So, and in fact, that actually segues nicely into what I want to say next, Rodrigo, is that we can also calculate the area using people call it the evaluation theorem, or people call it the fundamental theorem of calculus, where you find the area under the curve by anti-differentiating your integrand. So this is called, the function inside the integral is called the integrand. So we're going to anti-differentiate the integrand. We're going to get 4x squared over 2. I'm just using my antiderivative rule, my anti-power rule, where I add 1 to the power and divide by the new power, minus 3x cubed over 3 between 0 and 1. I should simplify. That's going to be 2x squared minus x cubed, evaluated between 0 and 1, which is going to be 2 times 1 squared minus 1 cubed. I feel like I made a mistake somewhere. Let me double check. I did make a mistake. So we'll get back to that in a second. We're going to see, we're about to find an error. That's all right. Minus 2 times 0 squared minus 0. So I end up with 2 minus 1 minus 0, which is 2 minus 1 is 1. We just said the answer was 3 before. So this makes me think I've made an error. And since this all was pretty easy to do, right? Like there's not a lot of room to make mistakes right here. It's probably a mistake I made on the other part. And if we go back, so looking at my work here, that looks right, that looks right, that looks right. That looks right, that looks right. Boom, there's my mistake. Should have been a minus sign. So let's fix that. So that should have been minus, 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 which is 1. It's good to check your work. Yeah, exactly. 2 minus 1 equals 1. 2 plus 1 is 3. 2 minus 1 is 1. All right. So these are some examples of
For a second.
oh yeah, sure. So these are both examples of essentially using the limit definition of the integral to calculate the area under the curve. And I'm going to go ahead and erase down here if that's all right. That's a lovely noise. So what I want you guys to be aware of is that the integral from a to b of f of x dx, although we can certainly find it doing what we've been doing with the fundamental theorem of calculus, can be defined with a limit. It's equal to the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k times delta x, where x sub k is any endpoint you want. We usually prefer the right endpoint. It's the right endpoint of the kth subinterval. And delta x is just your b minus a over n. Or more generally speaking, it is the width of each subinterval. And that is your limit definition of the integral. And that's what we've been doing in these last couple of examples, right? We found the f of x sub k times delta x. We wrote it as a sigma notation. We simplified it. And then we took the limit and got a real number that was the actual area under the curve. Okay. So I saw a couple of things here. One second. All right. So much like 21A, we spend a little bit of time finding integrals using this limit definition of the integral, but most of the time we're just going to actually use the nice rules we have. Much like how with derivatives, right? We spend a little bit of time doing the limit definition of the derivative, but then when things got more complicated, we had, the power rule and the product rule and the quotient rule and the chain rule. That's the same kind of thing that we're going to do here. We're not really going to do a whole lot of integrals where we have to deal with the limit definition. I mean, so it depends, Jason. Someone, and I certainly fall into this camp, I have definitely asked students in the past on exams to show the work of finding the integral using the limit definition of the integral. So it depends on how you're being asked the question. If someone wants you to do it that way, then no. But generally, yes. You can usually do the, if you want to find the area under a curve, you can typically use the fundamental theorem of calculus. So that kind of leads us to part of the fundamental theorem of calculus, or the FTC. That's the fundamental theorem of calculus. Part of it, there are actually two parts, but part of it says that the integral from a to b, the definite integral from a to b of f of x with respect to x is equal to capital F of b minus capital F of a, or as I usually prefer to write it, capital F of x evaluated between a and b, where capital F of x is an antiderivative of little f of x. Or you can also just say that. Yes, Sophia, the limit is the same as the area. It is not an approximation anymore. It is exactly what the area is equal to. The problem with the limit definition is that it's fine if your function is something that's a nice polynomial, like x to the second or x to the third or other higher powers of x. But once you start getting functions that are more complicated, like fractional powers or sine or cosine or exponentials or logs, it becomes very, very challenging to actually use the limit definition to calculate the area. So we used this already twice today, right? We did a couple examples where we did the antiderivative and then we plugged in the limit of integration to find the area under the curve. There's also another part of the fundamental theorem of calculus, but I don't think we're quite there yet, so I don't want to gum up the works. So there were a couple other questions asked. Somebody asked about finding integral of absolute value, and then also an integral with a square root. And I'm gonna have to, I might need clarification on the square one. So actually, I might need clarification on both. So here's what I'm imagining you're asking about for an absolute value one. Something like the integral from -2 to 5 of the absolute value of 2x minus, let's go with, sure, 2x minus 4. Does that look like whoever asked the absolute value integral request? Does that kind of look like the thing you're doing? I don't remember who it was. I can go back and look. Daphne. Oh, sorry. Sorry. I didn't mean to call you out. I saw that was a private question, but yes, I see some yeses. Okay, cool. Sorry. If you send me a private message, I will try to keep it private, but I don't think I've revealed too much here. Okay, so here's the thing. If your absolute value integral is the absolute value of a linear function, right? 2x, y equals 2x minus 4 is linear. Then you can do this a very easy way that doesn't require actually any anti-differentiation whatsoever. So here's what I'm going to do. I'm going to draw a picture. I know that y equals 2x minus 4 in absolute value. So I'm looking for the bottom of the absolute value, or the vertex, right? Absolute value functions actually also have a vertex, just like parabolas have a vertex. The vertex is, for an absolute value, usually where the function is equal to 0. What value of x, what does x have to be to make y equal to 0 here? Ooh. Yeah, exactly 2. Hopefully you guys all heard my lovely neck cracking there. Yeah, exactly 2. So when I plug in 2, I get 0. And I want to go from -2 to 5. So 1, 2, 3, 4, 5. And I know it's going to go like that and like that. And what I'm going to do is I'm going to plug in 5. So if I plug in 5 for x, what do I get for y? Nobody?
I didn't hear what you said.
Oh, sure. If I plug in 5 for x, what do I get for y?
6?
Yeah, totally. And if I plug in -2 for x, what do I get for y? Yeah, I get 8. So, wow, these sure look like some triangles. I'm just going to use my triangle area formula. So this triangle, I'm going to call it A1. A1 is 1/2 the base, which is 1, 2, 3, 4, times the height, which is 8, which is going to be 2 times 8, which is 16. And this triangle is 1/2, or has an area that is 1/2 the base, which is 3, times the height, which is 6. And 1/2 of 3 times 6 is 9. So the total area is 25. So I would say that the integral from -2 to 5 of the absolute value of 2x minus 4 dx equals 25. No integration required.
Is that, wait, sorry. Is that the same as saying that the limit is 25?
I mean, so yes, but um, I don't. How do I
They
say?
asked one time for like the limit of the Riemann sum. And then like I think it like kind of got the same answer if you did the integral. So I'm a little confused about that.
So you have a question that's asking you the limit of the Riemann sum, and it's an absolute value one.
No. Like it, like you did the area and it got the same thing. I'm not sure.
So I could write this as a limit of a Riemann sum. I don't want to. You don't want to. None of us want to. Sometimes we are asked to because it's kind of like the foundational building block before we get to do the next thing. Just like how we did the limit definition of the derivative before we got to use all of our derivative rules. And you could write this as a limit of a Riemann sum. It would look like this. The integral from 2 to 5 of the absolute value of 2x minus 4 dx is going to equal the limit as n goes to infinity of the sum from k equals 1 to n of my
-2.
oh yeah, thank you, of my function evaluated at my right endpoint times my delta x. In this case, my delta x is b minus a over n, which is 7 over n. And my x sub k is a plus k times delta x, which is -2 plus k times 7 over n. So I could write this as, it's going to be gross, the sum from k equals 1 to n of, my function is the absolute value of 2x minus 4. The x sub k that I'm plugging in is -2 plus k times 7 over n. So this is going in for x. So it's going to be the absolute value of 2 times my x sub k, which is -2 plus k times 7 over n, minus 4 times delta x, which is 7 over n. So you could write this integral as a limit. We shouldn't. We should calculate. So here's the thing. Yeah, exactly. It's way more complicated. The idea, basically, if you are asked to find an integral, a definite integral, also known as the area under a curve, you should do it in the easiest way possible. Sometimes that's going to be anti-differentiating both parts and plugging in limits of integration and getting a number. I will point out, when you're finding a definite integral where you have limits of integration, your answer is always going to be a number, right? Some amount of area. It might be negative if it's under the x-axis. It might be positive if it's over. It might be some, right? It could be 0, but it's always going to be a real number. It might be irrational. It might be gross, but it's always going to be a number. It's not going to be a function. This one, I shouldn't do that. I could, so you could also break this up into 2 integrals. You could break it up as the integral from, I'll run out of room here. For this A2, that's the integral from 2 to 5 of this line, which is y equals 2x minus 4. And then for A1, it's the integral from -2 to 2. But this line isn't the same as that line. This line is the line -2x plus 4. So you can also deal with an absolute value like that. But that's more work than I want to do. I want to do it the easy way. I want to use triangles, because triangles are easy to calculate the area of. So I want to re-emphasize, if you're trying to find a definite integral, you might have to use the limit definition if they ask you to, like in those homework problems. And if they do, it'll be a relatively easy function, like a linear function or maybe a square function. Usually they don't get more complicated than that. But if it's anything else where they're not specifically asking you to use the limit definition of the integral, you should find the area under the curve using the whatever tools you have at your disposal. Like this next one. Integral from 0 to 7 of the square root of 49 minus x squared dx. Eventually, we will learn how to antidifferentiate this function. At this point, I don't think any of us know how to. If you do, cool. But it's pretty complicated. There's an arc sign and some other stuff in there. So instead, what we do is we use our knowledge of geometry. This equation might not look super familiar written like this, but if I square both sides, and I add x squared over to the left, x squared plus y squared equals 49 has a pretty well-known graph. What kind of graph is that? Yeah, it's a circle. And the center is the origin, and the radius is what? And the radius is? Yeah, 7. So here's the thing. This equation and this equation aren't quite the same. In this equation, y can only be positive, right? Square root of a number only gives you a positive result. In this equation, y could be positive or negative. So in this equation where y is only positive, we're only getting the top half of the circle with a radius of 7. So if I'm trying to find the area under the curve between x equals 0 and x equals 7, I'm starting here at x equals 0, and I'm ending right here at x equals 7. So that's going to be all of the area under this curve. And that looks like a pretty well-known fraction of a circle. How much of a circle do I have? And what's the area of a circle? Pi r squared. So I get 1/4 of pi r squared, which is going to be 1/4 of 49 pi, or I suppose this is 49 pi. Or if you prefer a fraction, you could write 12.25 pi, but that seems weird. So that's how we can do one like that, right? We don't know how to antidifferentiate this, but we do know geometry. So a lot of times people will ask absolute value integrals and square root of things like this integrals, and their intention is for you to use geometry to figure out the area under the curve. Yeah. In fact, let me ask, who was it? Someone asked about square root things. Is this what you meant, or did you mean something different? Square root definite integrals. Cool. Yeah. So this is what, so yeah, I had to guess that this was probably what they were getting at. So let's see. What else should I say in the last couple minutes here? Is there anything else you guys would like me to really say before I just try and pick something? Well, I was going to look at the, no, I guess not. Okay, I know what I'm going to say. I got 4 minutes. Okay. So I did mention, now I should stop there. I should just, let's do one more example. So I want to find the area under the curve f of x equal to, what have we got here? Sure, x squared plus 3x plus e to the x on the interval from 0 to 2. Straightforward problem, but there's one specific thing I want you to be aware of. So I'm going to set up the interval. So the interval from 0 to 2 of x squared plus 3x plus e to the x. This is definitely not something I can use geometry for. So I'm just going to use my other skills, my anti-differentiation skills. I'm going to take another screenshot just to make sure I capture everybody here. I guess I can mute myself. That might work. Try that. Cool. Hopefully you guys didn't hear that one. I have to mute myself. Hopefully you didn't hear that one. Okay, so anti-differentiate, the antiderivative of x squared is x cubed over 3. Antiderivative of 3x is 3x squared over 2. And e to the x is great. The antiderivative of e to the x is e to the x. I don't need the plus c because it's definite. So now I'm going to plug in my limits of integration. I'm going to plug in 2. We get 2 cubed over 3 plus 3 times 2 squared over 2 plus e squared. And here's what I want to warn you against. Don't get into the incorrect habit of assuming that when you plug in 0, you always get 0. A lot of the terms will become 0 when you plug in 0, like all the x's to a power. But e to the x and cosine of x and lots of other functions aren't equal to 0 when you plug in 0. So when I plug in 0 here, I get 0 cubed over 3 plus 3 times 0 squared over 2 plus e to the 0. And that is 1. So don't make that mistake. I've seen a lot of people make that mistake over the years. When you plug in 0, you really need to check and see, are all the things actually 0 or are some of them other things? So then we're going to simplify. We're going to get 8 thirds. I'm going to cancel a 2 here and a 2 here to get 6 plus e squared and then minus 1. And then I can simplify this a little bit. I guess I would get a common denominator. 6 minus 1 is 5. So I have 8 thirds plus 15 thirds plus e squared. So I would have my answer as e squared plus 23 thirds. Or maybe 3e squared plus 23 all over 3. And I would definitely not get a decimal approximation, right? We don't want a decimal approximation. We want an exact answer unless someone specifically says to give them a decimal approximation. Yes.